And then we had DDP. So DDP was calling setup distributed, which was creating the TCP store. So we talked about the TCP store creations and how we rely on the cluster environment to extract the ranks of each processes when DDP is being running. I'm not going to recover that unless there is a strong ask from the chat. Anyone requires me to go back into how DDP works, or we explain that? Let's check. 5 people. Okay, I guess that's a no. So let's keep going on. Yeah, and here strategy was actually calling just the accelerator. Yeah, perfect, cool. You remember? That's awesome. Okay, so let's continue. So then the next step is setting up the profilers. So in Lightning we have several profilers. So we have the simple, advanced, PyTorch profiler, XLA profiler, and here we can see that all this logic lives within the trainer. So it's actually like a kind of hidden method where just to here initialize the profiler, here initialize like set up the profiler, and setup just means that there's some information we want to provide to properly instantiate the profilers, but those are not available when you create the objects, right? So until the user actually pass, let's say, the Lightning module, we don't know about it, right? So it's why, like here we have this way of setting up the profilers. One thing to know is the PyTorch profiler also works with DDP, which means like one trace is going to be computed for each ranks, and it's why the local rank is being passed to the profiler, so that's being saved automatically. So let's go back to the execution. So let's here continue. Okay, so then we have call setup hooks. So here we have like a small comment which is say allow user to set up Lightning module in an accelerator environment. So let's quickly look at what this one does. So here we can see we have this thing. I don't think we have seen that before. It's called a barrier, and the barrier is quite an interesting mechanism. So I'm going to quickly explain that. So that's actually implemented by most strategies. And the barrier is a mechanism which enables processes to wait to that point, like until all the processes haven't reached that specific line of code, then they will wait forever. And it's sometimes why when you train with DDP, if you have like a, let's say, a wrong condition, you can end up having a deadlock. So I'm going to show like a very simple example on how this thing could work out, right? So imagine you have some code being executed and you want to save your checkpoint only on rank 0, right? Because you have 8 process which runs, but you want to save that only on rank 0, right? So you could have something where you said if rank, so if is global 0, then do something else, wait, right? And that's a great example on how you could actually you could end up into like you multiple processes ranking, right? Because here you could save checkpoint, and then do something else here, right? And then you could actually go out and keep going with your life, right? But what's actually going to happen here if you do something like that, and here will be actually set.strategy.barrier, what will happen is if you're global rank 0, you're going to save, let's say, the checkpoint, and then you're going to do some stuff, and then you're going to keep going, right? But all the other processes are not global rank 0, so they're basically waiting here forever, right? Which means as global rank 0 is not going to come, those are going to wait, and the barrier is never going to be like the processes are never going to go out of this specific barrier. That's a very common mechanism to enable synchronization between your processes, because you know that all the processes will wait until they have all reached this specific line within your code. Cool, so let's quickly look at the race. So here we can see that we call the callback hooks setup methods, and then we call the lightning hook setup methods. That's primarily used sometimes when users have needs of customizing the lightning modules and they need to condition how the model is being created based on the stage. So that's where this logic could be implemented. So let's go back to the rest of the code. So we were here. Any questions so far? Okay, I guess we don't have any questions. Okay, so let's keep going. So here we have restore modules and callbacks. So this one is actually quite interesting. So when we are restarting, it's possible that a user provided a specific checkpoint. And if it does, it is a responsibility of the checkpoint connector to restart everything, right? So here there is a couple of methods that the checkpoint connector is implementing to do so. So there is a resume start, which is going to get the resume checkpoint path that the user provided, check that everything is done correctly, and if it is, you will actually load and validate the checkpoint, right? So here we have, as time passed, we introduced different ways of checkpointing. So maybe like there were like a different attribute which was stored in the checkpoint. So it's why here we can see we have like a specific patch which enables previous checkpoints to be reloaded. Then we have the restore model. So restore model will do what you expect. It will call the on middle on load checkpoint hook and provide the full checkpoint. It will then load the model state dict, and that's actually the responsibility of the strategy here. And there is a good reason for that. So in Lightning, we have two different mechanisms of saving a checkpoint. So I'm going to quickly draw that. So we have, let's say, the strategies, which creates one checkpoint for all ranks, right? So imagine you have multiple processes. There's still only one checkpoint which is created, and that will be rank 0 responsibility. We have other strategies in Lightning which saves n checkpoints, which is equal to the number of processes you actually have running, right? So you get n checkpoints, actually you get word size checkpoints, right? And those strategies are deep speed, for example, 0.3, FSDP. And what the strategy do are around sharding. So when you scale to very large models, the traditional way to do so is to take every parameters of your models and slice them and give the chunk to each process. So I'm going to give a small example here. So imagine you have a linear layer, which is, let's say, 100 by 100, right? And you have two processes. So what will effectively happen is when this layer is instantiated, as soon as it is, so first step, we instantiate that one. Second step, we chunk that weight, right? So here we have 100 by 100, and here we have only two processes. So we are going to create 2 times 100 multiplied by 50, right? So that's going to be the parameters that each process is going to receive. So one process effectively will be owning 100 multiplied by 50 parameters, and the other one will be owning 100 multiplied by 50 parameters, which means that each process will be saving its own chunk of the parameters of the model. When we do a forward, and I think actually maybe FSDP, I don't know if I can find that back, so let's see if I can. I think they had a good diagram to explain how a distributed training works, so let's see if they still do. So if people have never heard of PairScale, it's a very cool framework from Facebook research. It's really pushing the limits of what's being done right now with PyTorch, so that's actually quite interesting. So let's see what I can show here, if I can easily find. Okay, is it this one, slow-mo? Okay, I didn't look into that. Let's say checkpointing. Okay, so they have like the distributed parallel here. Okay, seems quite interesting. Okay, so here they have a sharded data parallel. That's maybe the latest implementation. Okay, they had, yeah, I'm sorry for that. Maybe I can try to find it back from the, okay, let's see how I could find it back, right? So that's also, I guess, a good trick for people who, let's look for FSDP. So here I'm looking at all the PRs that has been closed, and hopefully I will see something. I think it was interesting. Okay, so what I'm effectively looking at, so what I'm trying to find right now is the first PR ever merged to, okay, I think it might be this one. Let's see if it is. Yes, awesome, cool. I found back that PR. Let's see if I didn't lose everyone. Yes, I did lose some people while doing it, but that's cool. We came around to see the first PR from Miles, so from Miles from Facebook, who worked on FSDP, right? So that was like the first like big PR that people made. It's beautiful work. So everyone who wants to have a look at it, I'm going to share this PR. Yeah, definitely, yeah, I can do it. Sorry for that. But yeah, you can find it under add fully sharded data parallel FSDP PR. So let's quickly, I'm going to quickly explain how that works, because I think it's quite a fascinating thing to look at. So here is actually how it works, right? So here's the standard data parallel training. You have some datas. You are going to chunk the datas. You have the same model on which is owned by different processes. And what you effectively do is you are going to call forward locally on each process. And here we have different colors because we have different activations. Like the data were here different. So even if the weights are the same, the activations are different. Here, effectively, we have the same. We do backwards, the loss was different, therefore the gradients are different. But now, when we do a sync grad, the gradients become the same, right? Because we reduce the gradients across those two processes, and now we are in sync. Now those weights, those gradients are the same, which means that when I make an update on the weights here, I'm actually I actually have the same weights, and now I can restart again, right? So that's like the entire process behind the standard data parallel training, right? So let's look at the fully sharded data parallel training. So as I said, the idea behind sharding is every time you have some parameters, actually, or a linear or a layer, so an NN module, you are going to divide it. So you are going to chunk the parameters and divide the ownership of those parameters by chunk to the current processes. So here's how it works, right? So what happens is when you get the datas, so you get like here a different batch of data on each process, you have the shard of the model. So it means each process have only its own chunk of the weights. When we do the forward, and here we can see that there is n layers. So this operation here is called n times, right? So here we have this single block. Here now this single block is being split into n layers, and n, so one layer is the maximum amount of parameters I can fit on my GPU. And here we are talking about massive models, like billions to trillions of parameters. So effectively it's as much like one layer would be considered as all the parameters you can fit onto one GPU until you raise an out of memory error. So what happens is you call an operation, which is all gather, because what you own is actually a chunk of the data. So what you need to actually compute the activations is effectively the entire parameters. So you are going to perform an all gather. So you are going to reconstitute the entire parameter, perform a forward, get the activation, and delete the full parameters, right? So you pull the parameters, you make the computation, you delete the parameters, and you keep the activations, right? And if you really want to optimize for memory, you can also move the activation from GPU to CPU, or you could recompute the activation actually post during the backward propagation. And I think that's what we actually call offloading checkpointing, which is we offload the activation computation during the backward, right? So here what happens effectively, if you want to really maximize the size of the model, you gather the parameters, you make a forward, you drop the parameters, you do that n times until you get to the loss. And now you do exactly the same, but for the backward, which means you get back the weights, you perform a backward, potentially you also compute the activation back, right? So compute the activation, do backward. And what you get here is a full gradient. So you get a full gradient locally for your entire parameter, but what you own is only a shard of that model. So what you do is actually a reduce scatter, which means you reduce the weights across all the processes, exactly as we will do here, but then you remove everything that you don't own. So you just keep a chunk of the gradients, exactly in the same way as you had the chunk of the parameters. And that's the algorithm they have here. So in the traditional way, when you do a all reduce, you get some tensors which are different, right? And what you effectively do is you sum them out, right? So here you do all reduce on the gradients. What each rank is going to see is a reduction of all the other ranks plus itself, right? But when you do actually the reduce scatter operation, it's slightly different. You actually get, so every process has only a chunk, right? And what you end up doing is you all reduce everything, right? So you all reduce all the gradients because every process starts with only a chunk, right? So you all reduce all those parts, and then you just keep only what's yours. Any questions about it? Any questions about FSDP? Okay, I guess no questions. So just for people knowledge, the concept behind deep speed and deep speed it's very similar. So it's with same mechanism of gathering, computing activation, dropping it. It's just that very optimized. So yeah, definitely some very interesting works which has been done there. So let's go back on the trainer. So here when we do restore models, it's why the strategy handles the reloading, because deep speed, for example, has its own mechanism to reload the checkpoints, right? It will actually restore it, but that's relying on its own internal mechanism. So what is the difference between activation and gradient? So activation is what's being computed from the input and through the weights. The gradient is what's being derived from the loss to the gradients, to the weights. Gradients are used to update the model weights. Yes, exactly. The weight are used to update the gradients. Okay, cool. So yeah, here we are. For example, we can see that, and that's actually a very nice piece of code. If people want to check it out, I think that's actually quite beautiful. So here in the load model state dict of the deep speed strategy, yes, exactly. right? So model equal input simple activation, but then you compute your loss. And when you call loss.backwards, it's going to apply the backpropagation rule, and the gradients will be complete, like the gradients will be the derivative of the loss in respect of the weights. Cool. And here we can see, for example, that as the weights are as the models was sharded and saved to the file system, when you want to reload it, it's very likely that it will be in the same way, and therefore you need to reload the weights. And here we see that there is this gather parameters which goes through every parameters, reload the weights, but then this one will be responsible for the sharding automatically the weights, which I think is actually very nice. And here we can see manage a gather and partition of the parameters of the current layer, then load the state dict, and then we partition them again. So yeah, that's actually quite nice as a mechanism. Okay, so here we have restored the module. I'm just going to check that we have covered everything. So yes, the strategy will add the modules. Here we reset the metrics. Then we are going to restore the data module. So what does that mean? We just call the hooks on the data module on loads checkpoint, load state dict. And then the last piece is here we restore the callbacks. So here we are going to call callbacks on load checkpoint, which is, so let's look for this method, right? So we can see that we are in the checkpoint connector, but that method actually belongs to the trainer. So that's something we could argue is not necessarily required. So let's see what's happening here. So it's so we get the checkpoint, so we get all the callback states. We check the version, so here we can see that callbacks might have changed, and it's why we are checking some legacy stuffs. And what we effectively do is for every callbacks which has been passed to your trainer on restart, we are going to find its like the associated state within that dictionary, right? So here we have a dictionary which maps either like a type or a string to the state of the callback, right? So here we are going to get the state key and get the legacy state key, right? And get the state, and if that state is actually defined, we reload that, right? So here by looking at the code, we see something which is actually quite interesting, is if we want to actually reload our code exactly as it was from a checkpoint, we need to provide exactly the same callbacks as when we train, right? So if you were to do, let's say, the following, like imagine you create a custom callback. And here we can see this custom callback need to implement some hooks, right? So if the callbacks was implementing the onload checkpoint, so here it gets its on state dict. All right, so here I get a dictionary, and it was implementing the on save checkpoint. And here was, let's say, returning some stuff, right? So imagine it's returning something. And I'm actually training with that, right? So imagine now I'm actually creating my trainer, and I'm creating my callback. When you restart, so here you have trainer, right? And here you have trainer.fit, and now you train, right? And then when you restart, you might want to, you would have to, let's say, recreate a trainer and provide like the best, like the previous best model, for example. Here, if you were to actually run it without that callback, here when we restart, what will happen effectively is that list will be empty, right? Like the callback you had when you trained the first time won't be there, and therefore you won't be able to restart properly, right? So it's why if you actually check some of the callbacks within Lightning, which I think might be stateful, so let's check fine-tuning, for example, they have to implement those hooks, right? And they will need to be provided back when you restart. So here we can see that, for example, this one, let's say the base fine-tuning callback, which is used to, let's say, fine-tune a specific backbone of your model, implement the onSave checkpoint and the onload checkpoint hooks, right, which are called when saving the checkpoint and when reloading it. And what's, for example, returned here is all the internal optimizers metadatas, which are being used to progressively unfreeze some of the parameters of your model. Any questions so far? Am I going too fast? Okay, cool. I can see 4 people currently there. Any questions? Okay, cool. Speed is fine. So let's go back to... Okay, so I'm not sure exactly what this method was called. So let's try to find it back. Okay, so we were here in the checkpoint. So here, let's go back, right? So here we were in with our callbacks. And then we were in the restored method. So here you can see that you can quite quickly navigate the code base by just like kind of looking for specific methods by just adding the dot, or like sometimes the dot self, right? As you know, that's likely things will be called this way. So here I can see, okay, now we have restored the callback. We are also going to restore the training state. So training state means restoring the precision plugins state, right? We are going to also restore the loops. So the loops have also the on state, which is, I think, quite fascinating. So it's actually the progress of the loop, which is stored in those states. And then also, if you are training, or if you are in the training stage, then the optimizers and schedulers will be restored. So here we can see we restore the optimizers and then we restore the schedulers. So let's look quickly at what this code does here. So that's actually here we can see that restoring the optimizers is actually the responsibility of the strategy, right? So if we want to understand why, again, we can just like look for this specific method and see that, oh, okay, it's implemented on the base strategy, right? And we get the optimizer state, and then for all the optimizers that the strategy owns, we are going to reload that state and we are going to move it to the current device, right? But we can see that deep speed is a bit different, right? And here deep speed actually doesn't reload it here. And we might be, oh, wait, that's weird. Like deep speed doesn't reload the optimizer state, right? But again, deep speed is particular because when here we save the checkpoint, it's actually going to save the entire modules, but also all the optimizer state. And that's because the optimizer states are also sharded, right? So deep speed is actually responsible to handle all this logic. And when we reload the checkpoints, deep speed actually reloads here. And here we can see that deep speed is actually as a property, right, to decide if he wants to reload the optimizer state and if we want to reload the learning rate scheduler states. Cool, so here we add this method. So let's go back now. So I think I was here, so let's find, okay, so I'm going to go back to whatever this method was called. Right, so I was here, right? So restore optimizers, we have done that. So that was restore optimizers and schedulers, and here we have the restoration of schedulers. So everything in Torch is really stateful, right? So here we have the same thing. We restore the schedulers, and that's really important when you have some like specific learning rate scheduling schemes that you want to make sure you maintain, even when you train for a very long time. Okay, so we went through, I think, all the restoration part, which I think is quite cool. So let's go back here. We were in training step. All right, and here we restore up. So this method was called from. So if I'm looking for a specific file, I know I was in the trainer, I think, when that was called. So yes, I was here, right? So let's look at what this one was called. Okay, so everything started from here, right? So I found my way back by just looking at the function calls, by going deep and then going up. Any questions on the restorations of the modules and callbacks? Okay, 4 people, that's great. Okay, I guess not. Okay, so now we have the call configure sharded module hook, and here, as you can see, we have a couple of interesting things. So we have this context, which is model sharded context. The configure sharded context is something which, so let's try to find it out, right? So let's find which strategy implements that, and again, that's going to be the sharding one, so that's going to be fully sharded, right? So fully sharded as this enable wrap context manager, which is going to be responsible for every time you create a parameter, it's going to shard it automatically. So it's going to do what we saw right here. It's going to just okay, interesting. Yes, it's going to just shard the modules and have them fully splitted. DeepSpeed has its own context manager, which is DeepSpeed 0 init. And this one will be responsible for the same thing, like every time a parameter or an module is being created, its parameter will be automatically sharded. So here we have another thing, which is handle meta model. So that's actually quite an interesting thing. So in PyTorch, we have this idea of a meta device. It's like the terminology is not really fully defined, I guess, but I think the PyTorch team is going toward deferred parameters. So the idea is, imagine you create like some, let's say like some massive matrix, right? So you create this 1 million by 1 million matrix full of zeros, right? If you create that, right, and I think here you could even say, so you could like device equal CUDA, if I'm not mistaken, right? If you do that, it's very likely that this matrix is so big that it will break on your device. And what's really interesting is there is this idea of meta device where this tensor is going to behave exactly as a real tensor, but it's actually not materialized, which means it doesn't take any space. It's just like it's a lazy tensor, right? But the thing which is really interesting is it behaves very similarly to an existing one, right? Because you get the shape from it. You can you should be able to do something like that, right? So you should be able to have y equal x y2, and then what you could have is you could say materialize, right? And I think that's not exactly the right terminology, but what I'm trying to convey here is if you do that, then the operation before will be materialized, right? Like they will actually happen. So here we have this idea that an entire model, which is way too big to be defined, can still be defined into like a meta, into a meta way. And here we actually enable to materialize the entire module automatically under the sharding decorator, which means that every time any model is effectively going to take storage space, it's going to be sharded, right? So if you wonder why this thing happens, here we have this on meta device, right? So everything is actually inside of this file, the meta. And here we have the context manager to be used. So if we want to check why that's being used, we have some, can check that why that method is being used. And here I can see that we have some test right here why this thing is being used, right? So for example, here I have a borrowing model, right? So I think we can even look at this one, right? So here, for example, you could do the following, right? So you will say, create a linear layer, and I can verify that's a linear layer. When I check the device type of its weight, I can see it's a meta device, which means that it's actually not there. It's not physically on my machines, right? I can check that it's actually a meta device. I can even create like a more complex MLP if I wanted to, same on the device. But now if I do materialize, that will exist and the weight will be visible, right? which means that you could create a massive model under this init meta context. And now you get to a place where when you actually materialize it, right? So if you were to do, let's say, you initialize it this way, and then if you were to say with deep speed, let's say sharding, right, context manager, if you materialize the model now, then you have a very nice API where the only thing you had to do was to define a massive model and it will be automatically sharded, right? And that's actually what one of the features that Lightning provides with deep speed is the ability to create the model and then to use a deep speed strategy with stage 3, and your model has been defined as a meta device, but then when it starts to run, then now it's actually training on GPUs, and here we can see that we are training on 2 GPUs, and everything just worked fine. So yeah, very, very interesting things there. So that's happening here, and also here we call some hooks for the NN modules of the user to be defined under those hooks if the user has some sharded models. But I do recommend to use this decorator to create meta modules because it just makes the entire process much simpler. Any question around meta devices? Let's see. 3 people, some people are leaving, that's okay. Cool, so now we have called these hooks. Can you share the documentation for meta tensors? Yes, so on PyTorch, if you put meta tensors, you might see, yes, here you can see is meta. I mean, I'm sure if you Google around, you will see more things on meta tensors. I know they are changing stuff right now, like they're trying to find the best API to enable, like to make sharding very natural. So I think things are still moving around, but that's still a very interesting thing. I think on Lightning side we have I don't know if we did yeah, I'm not sure, I don't find it here, but anyway. Yes, so yeah, meta tensors are something around in the PyTorch code base, and here we actually rely on some core work which has been done from the PyTorch team on how to support those things. Okay, so let's keep going. So here we have some, like here we have a small piece of thing, like a small doc string to help users to go through like the different things and explain how it works, right? So here is actually the core of the loops, right? So it looks like that. You call fit, test, predict, or validate. And first we spawn the processes, so the processes are being created. We have the setup environment method, which is being called. Then we have run stage, and run stage dispatch to run train, evaluate, or run predict. So I'm going to move a bit faster because I know we have 10 minutes left and I didn't even get to the loops. So looks like I can talk about Lightning for for hours. Yeah, so here we can see we reset the metrics, we reset the results. So like a little bit of cleaning that's really meant for you when you call fit multiple times. You want to make sure everything has been restarted. Here we set up the strategies. So here we can see that configure model and move it to the device. People who have, again, who have some interest, you just put setups here and you check, let's say, strategies. Right, and here you will see all those different methods being implemented. Sometimes you can also do that, so you can match exactly that method, right? So I think a skill that users, like software engineers, sometimes underestimate is the ability to navigate a code base, or just like, you know, like if you're really looking for this specific pattern, right? So if I was to just do that, I will get a lot of case I don't care about, like setup distributed, right? But if I do that, now I just get the case I care about, right? So it's using the strategy, and I know there is, because I looked at the code base first, I know there is a strategies directory, And now I can filter all my answers based on that. So I can very quickly check that all those different strategies implement that. And here I'm talking about Lightning, but I think it will be true for any frameworks. If you really focus on how you search the code base, you will get much more efficient at learning a specific tool and understanding how the code base has been structured. And it's why I think the first thing ever you do when you look at any code base is just browse the files and the directories, right? Because here, by just saying that there is this strategy objects, I remember there is a strategy directories, and now when I search, I can filter to look only within the strategies directories, right? And that makes the entire process much faster for me to understand what are like different ways I can set up the I can set up training, right? And here, for example, if I check the setup of DDP, I can see that there's a couple of things which are done here. I have a mechanism to detect for deadlocks. So here we have something which prevents, in some case, the processes to hang. We move the model to the device. We support layer synchronization for batch normalization. And here we have this configure DDP, and configure DDP runs a couple of hooks. So we have the pre-configured DDP, which is going to like prepare the calcs for DDP wrapper. So let's just go back to that. And here we can see we have the setup model, right, which is going to wrap the model into a Lightning distributed module, which then is going to take this thing and wrap it into a distributed data poly. And that's actually a very interesting thing for people who wants to check this out, right? So here what effectively happens, and we can see that becomes the model of the strategy, right? So past the like once configure DDP has been called, the self.module is not the Lightning module anymore. It's actually the Lightning module which has been wrapped into a Lightning distributed module, which has been wrapped into a distributed data parallel module, right? So here we can see we have this nesting of responsibilities, which is quite intriguing. And if we check what this Lightning distributed model does, is actually not too complex. So here, let's see what it does. So it's actually a wrapper. And we can see that what happens is when the forward method is actually going to be called, that object as a reference to, we can extract the trainer, right? So the Lightning module has a reference to the trainer. And with it, we can route, right? So if the trainer is defined and we are actually training, then we will be calling the training step of your Lightning module,